All right, hello, welcome back. We are going to look at Theorem 1.6 here. I think it's a pretty important theorem. We're going to use it in proofs. You're going to want to know it for proofs that you write as well. So, the examples that we were doing previously are sort of to illustrate this theorem as well as illustrate how to write the null space as a span. That's why we're doing a bunch of these examples, because these are things we're going to use a lot. So what theorem 1.6 says is that a list of vectors is linearly dependent if and only if one of the vectors can be written as a linear combination of the others. And specifically, if W is linearly independent and a1 is not 0, meaning the first vector in the set is not 0, then some ai vector with I greater than 1 is a linear combination of the preceding vectors, like the ones before it. So we're not going to prove it. We just want to give you an idea why it's true based on the examples you've seen, because it's a lot easier to remember these theorems when you know why they're true. If you try to go through this class like memorizing everything, it's going to be miserable. You want to understand the concepts, and then once you understand them, you'll be able to rebuild what the theorem is with your understanding of it. So as an example, example one, the first one we did here, I just copied and pasted screenshots for all these. This list of two vectors, by the way, the list is technically a1, a2, same idea as the matrix that has those columns. Anyways, a2 you can write as 4/3 times the second one. So one of them is a linear combination of the other one. So according to this, it should be dependent because one can be written as a linear combination of the other. And this solution of this equation, like the 1 and 4/3 here, goes along exactly with the definition of linear dependence, that you can get the 0 vector with non-zero coefficients here. Example 2 was a little bit more complicated, but we found the only way to get the 0 vector is with the trivial solution where all of the coefficients here were 0. And we explained why no vectors can be written as a linear combination of the others. Because if you could, that would result in a non-trivial solution to the homogeneous equation existing, and we know there does not exist one of those. So another way to visualize this is, well, let's remember what example 1 looked like real quick when we looked at the span of a1 and a2. Like the two vectors were on the same line. They're in each other's span. And with a2, it's harder to visualize why that is. I would totally fail to draw a picture of it, so I used Desmos here to help. So what I did here is I just took the vector -1 to -1, and then Desmos, that is here as this red point. So that red point is where x is -1, y is 2, and z is -1. And the blue one is -3, 5, -2, the a2 vector. So a2 is the blue one, and a3 is the point 1 to -1, which is here. Okay, so we've got these 3 points. And what I also did is I figured out for each of them what is the equation of the plane that goes through the origin and a pair of 2 points. So for example, here, this blue one, or purple one, is the span of a1 and a2, the red and blue points. So you can see that a1 and a2 are not exactly on a line through the origin. They're close. But because you can go, like, when doing linear combinations of that red point and blue point, you can go a little bit sideways from each other. The span of them ends up being this whole big plane. And notice that that purple plane does not include the green point here. So the span of A1 and A2 does not include A3. So A3 cannot be written as a linear combination of A1 and A2. Likewise, if we look at the span of the red and green points, which is A1 and A3, that's this gray plane here. That does not include the blue point. So, in other words, A2 is not a linear combination of A1 and A3. And likewise, if we get this green plane, that does not include the red point. So that is the span of the green point and the blue point. The span of A2 and A3 does not include A1. So none of these three vectors can be written as a linear combination of the other two. And also, we did show that the second thing is false here, that no AI can be written as a linear combination of the preceding vectors. Okay, example 3, this was a linearly independent set. A1 could not be written as a linear combination of the other none vectors. There are no other vectors. Okay, example 4 was one that's kind of a weird case because this is linearly dependent. For example, we got a non-trivial solution to the homogeneous equation, and we saw how the points lie sort of within the same line. A1 is not really separate from the span of A2, but A2 could not be written as a linear combination of A1. So what that means is that this thing, that some vector AI with I greater than 1 is a linear combination of the preceding vectors, that part is false here because A2 could not be written as a linear combination of A1. But what the first part of the theorem says is that it's linearly dependent, which it is, if and only if one of the vectors can be written as a linear combination of the others, and A1 can be written as a linear combination of A2. So A2 is not a preceding vector of A1, but this thing, the second part of the theorem, doesn't apply here because when the first vector is 0, then yeah, that part doesn't work. But at least one of the vectors is on the span of the other one. A1 is on the span of A2. So that's that example. All right, that was a quick video just talking a little bit more detail about that.